See my slides? Can you see my slides? Okay, I'll take. Okay, thank you. Okay, hi everyone. I'm Rohit Kumar Singh, teaching assistant for Experimental Physics 2 course, and the tutor of the course is Mal Kumar Das, and you can go through the lectures of this course over NPTEL. And in this live session, we will recap some of the materials of the course and try to solve some sample problems which will help you in the tutorial assignment. Okay, yeah, this is the second live session. And, okay, let's start. Today mainly we will discuss some problems related to atomic physics and some concept related to significant figures in the measurement. Okay, and so if you remember last time we discussed about the measurement, I mean the errors in the measurement and different uh, tools for precision measurement like vernier calipers. Okay, so I have just for a recap, I have kept one two problems on the error calculation. So let's go through them first. So the first problem is here. Uh, so the question is the error caused by poor calibration of the instrument is called. So there are four options: random error, systematic error, absolute error, or relative error. So what do you think will be the correct answer? What do we call the error caused by poor calibration of an instrument? Any guesses? Sai Teja, what do you think? B. Systematic error. Okay. Others? Parshuraman, what do you think? Okay, now let me say C. What about Parshuraman? What do you think? Okay. So, yeah, the correct answer is actually B. So, it's called systematic error. Oh, Parshuraman says A. No, A is not correct. B is correct. So, it's called systematic uncertainty. So, what happens is that sometimes suppose you are measuring something with an instrument, okay, and that instrument itself is not well calibrated. So For example, in the last lecture I mentioned, like in the vernier caliper, what we can uh, what we sometimes observe is the zero of the main scale does not coincides with the zero of the vernier scale uh, in the starting, and that's a calibration problem, right? So that type of, I mean, it's a simple example. So in a very huge experiments, like the experiment that which in which I am involved in. So I'm involved in an experiment called compound muon solenoid experiment. It's at CERN. So there, it's a very huge detector. Okay, basically, and there are many different components and many different submodules, and so it's very difficult to calibrate all of them accurately. So there is always some calibration, uh, you know, calibration mistake, and those kind of errors that comes from the calibration, uh, poor calibration, uh, they we call them systematic error. And there are various methods to how to account for systematic errors. So just to keep this in mind, it comes due to calibration. Okay, then a second problem on error. So first of all, what is random error? Anyone? No. First, tell me what do you mean by random error? Can anyone tell me? And how is it different from the calibration error? So okay, so let me let me explain. So just now I told you that the random error, the systematic error is due to the calibration uh, problem in this. So suppose you have a zero error in the vernier caliper. So whatever you are measuring, so suppose you have positive zero error, okay, in your vernier caliper. Now whatever quantity, so suppose you are measuring some diameter of a thin wire, okay, and the diameter comes out to be 0.02 mm or something, okay. Now if you have a positive zero error of suppose 0.001 mm in your vernier caliper, it will always your so suppose this is the true diameter of the wire, but when you will measure with this vernier caliper, what you will get is this quantity, okay. So it is overestimating the result, okay. And whatever you will measure with this vernier caliper, it will always overestimate it. Okay, so the error is in one direction, right? It is unidirectional. So systematic error is unidirectional. Okay, but the random error, it can be in both directions. Okay, so uh, suppose this vernier caliper has some loose screws or so anything. Okay, first when you measure the diameter, it came 0.022 mm. Okay, then again you measured it was found to be this quantity. Okay, so these kind of this kind of measurement errors which can happen in both direction. Okay, it's called random error, and this can be caused by various things. So suppose if your instrument is not you know has some loose screws or some some problem is there, some manufacturing defect is there. uh, it can be also caused by the way you are measuring. Sometimes because we don't have perfect hands, so many things can go wrong. So how do we account for such error, right? For systematic error, as I said, there are various methods. So suppose you can calculate the positive zero error, and then you can subtract it from whatever your measurement is. So in that way you can account for the systematic error. But for the random error, uh, how can we reduce it? So yeah, now please tell me your answers. So Mahalakshmi says, by taking a large number of readings of different observers. Okay, anyone else want to try? So yeah, Mahalakshmi, you are partially correct. Uh, Obviously, we can take a large number of readings uh, and see. And then so just taking a large number of reading is not enough, right? When you are so suppose you are measuring like here we are measuring a diameter of the wire. Okay, and in only two readings we cannot tell anything. So we will take suppose 10 readings. Okay, and then we'll have a 10 sets. We'll have a set of data for the diameter, and then you'll have to do some statistical analysis, like taking average of those values, or taking square mean root or whatever. So that we can reach to a certain conclusion that yeah, this should I mean uh, the random error is not greater than this. We can take a standard deviation from the mean or something, right? So so we'll have to do the statistical analysis also. So these both these steps are necessary to reduce the random error. Okay, so do you understand what I'm saying? So suppose uh, what you do is you will take suppose 10 uh, 10 measurement of the diameter, and you will plot it uh, here. So this is the diameter, and you will plot it. Okay, so you can get sometimes your value is this, and you can get a Gaussian or some shape you will get, right? And then the mean will be the, I mean, you can calculate a mean and then there will be some standard deviation. So this standard deviation uh, can be used as the error. Okay, this can be quoted as the error, which is a random error. So like this, you can reduce the random error. Okay, so both option A and B is correct. So I hope you understand what I'm saying. So if you have any doubt, you can ask about random or systematic error. Is everyone okay? Everyone understood? Okay. If there are no question, let's move to the next problem. So yeah, this is a simple question. So I'll assume all of you have basic knowledge of atomic physics from class 12. Yeah. So the question is, who gave the quantum theory of light? So option A is Albert Einstein, option B is Heisenberg, option C is Michelson and Morley, and option D is Max Planck. So yeah, uh, any guesses? Sai Teja says it's D, Max Planck. Anyone else? Mahalakshmi says A, Albert Einstein. Okay. Anyone else? No one else want to try? Okay. Parshuram says A. Okay. So, two votes for Albert Einstein, one for Max Planck. So far, Albert Einstein is winning. Anyone else want to support Max Planck? Okay, so yeah. So actually, the winner is Max Planck because this is not democracy. This is physics. So yeah. So Max Planck gave the quantum theory of light, not Albert Einstein. Albert Einstein also did a very important, uh, gave a very important theory which is called photoelectric effect. I don't know if you guys have heard about it. Photoelectric effect. So this is also a very major uh, step in the quantum in the evolution of quantum physics. But the starting of the quantum physics was done by Max Planck. So Max Planck gave this quantum theory of black body radiation. Okay, so okay, I'll explain it a little bit. What does it mean? So what? So Max Planck was trying to calculate, the uh, so so okay. So you all know what black body is, like. So black body is a system which absorb all the frequencies of the light. Okay, so and it also emits all the frequencies of the light. So it's so because I mean, it is absorbs all the frequency. It it has no color. It's black. Okay. So, I mean, it's a theoretical model. Uh, you can try to make a black body experimentally, but it will not be perfect. Okay, so theoretically, one can do the calculation of energy density. So we call it spectral energy density. Okay. So this is the energy density per unit. Uh, so U is the energy density per unit frequency range, and when we plot it as a function of frequency, so if we don't include the uh, quantum theory, yeah, yes, I tell you, you are right. Meets all wavelength of frequency. Uh, so if we don't consider the quantum theory, and if we do our calculation based on classical physics, okay, uh, the plot that we get is something like this. So it goes like this, and then at higher frequency it shoots up to the infinity. Okay, so this is done using the Rayleigh Jeans formula. Okay, but this is not the case experimentally. Experimentally, one sees that uh, the at higher frequency the energy density comes down like this. Okay, so to explain this curve, what Planck did is, instead of taking the energy as a continuous entity, he took it as a quanta. So uh, he put in the place of energy h nu. So h is the Planck constant, and nu is the frequency of the light. Okay. So what he proposed is, light is made up of small quanta called photons, and those quanta has the energy h mu. Okay, and then uh, he substituted. So this is the formula for the spectral density, and this if you plot this as a function of frequency, you will get this curve like this. Okay, and so this is called the Planck uh, radiation formula. Okay, so from here the quantum physics took off, and then came the photoelectric effect, then came the Heisenberg uncertainty principle, and many things, Schrodinger equation, like that. So, but the starting point was this plot. Okay, okay. Then anyone has any question here? Okay, if not, then let's go to the next problem. Okay, so the next question is on the atomic physics. So suppose hydrogen atoms are excited from ground state to the state of principal quantum number 5. Then the maximum number of spectral lines that may be observed is. Okay, so here are the options. So what does this question mean? So we know that the all the atoms have some energy levels, right? We have this ground state, excited state, third excited state, and so on. So here the question is, uh, if we excited the electrons in the hydrogen atom from ground state to uh, fifth excited state, that is the where n equal to 5, and then what will happen, right? So what will happen, the electron here uh, will try to come down, right? It will de-excite, and it will emit a photon, right? You all know that. So but it can either it can come directly to ground state, or it can come to first excited state, can come here. So so in this way there can be many possible spectral lines. Okay, so what is the maximum number of spectral lines uh, that can be observed? So how do you calculate this? So there is a general formula. I'll write this. Maybe you have seen it. So this is the formula, and here n is the highest orbit, n is the lowest lowest orbit. So for our case, n equal to 5 and n equal to 1, right? Because we have excited it from ground state to fifth excited. So for this we have, and then we can calculate the number of lines. So if you put n equal to 1 here, this formula becomes n minus 1 by 2, and which is, when we put 5, you will get uh, 12, right? Sorry, you will get 10. And this you can also see. So suppose you can calculate it by hand. So let's do that. Let's see if it matches with our calculation. So from 5 it can come to 1, right? 5, 4, 3, 2, 1. Can come to 4, 3, sorry, into 3 and 4, right? Then what can happen is uh, from here it can again goes it can go here, here, and then here, right? So 4 and 3 plus 7. Then from here it can go here and can go here, right? And from here it can go here. So you can count the lines: 4, 3, 7, and 3, 10, right? 10 number of spectral lines. So this is how you can do it by hand. But suppose if you have a number like n equal to 10, then it is very difficult to calculate by hand. So this formula comes in very handy. Okay, so yeah, it's so the answer will be none of this. Simple problem based on this formula. Just to remind you. Okay, then let's go to the next problem. Now, uh, this is on the radius of uh, the orbit. So the radius of the Bohr orbit depends on which of the following. Okay, so we know that uh, in okay, Sai Teja asks, insert in this problem what is the value of n can take. Uh, you mean here what n can take? N can take any value, right? But always n should be greater than n, right? N can take any value. From 5, it can come to 2, it can come to 3. So this will be your n. But n cannot be greater than 5. I mean, it cannot be 6, right? Because then the energy conservation will be violated. So, so we have excited it from 1 to 5. Okay, how can it go from here to 6? Then again we have to provide some energy to make it go further up. It can only come down to either 4, 3, 2, or 1. Right? Okay, so next problem. So, so we know that the atoms inside the atoms, the electron moves in a fixed orbit, right? And the radius of the orbit it depends on the principal quantum number n. Okay, so but here we are asked what is the dependence on n. Okay, so what is the dependence of n? There are four options: 1 by n, n, 1 by n square, n square. So anyone of you know what is the answer? C 1 by n square. Okay, so let's derive the formula of the radius. Okay, rather than just telling you the answer, I'll just try to derive the radius of the uh, orbit of the electron. So suppose this is a hydrogen atom. Okay, here we have electron. So this is a very crude model, and this is the nucleus, which is just one proton, right? And its charge is E plus, and its charge is E minus, right? So there will be a Coulomb force between these two, and which we can write as, sorry, electric force, which we can write as right, where r is the radius, correct? And there also will be another force, uh, which is centripetal force, because this is moving in a circle. So the centripetal force will be on this electron will be mv square by r, where v will be the velocity of this electron, right? And to and these two forces should balance, otherwise the atom will not exist, right? So these two should be equal, and it is this, and here r cancels out, and you have the expression for r in terms of mass and velocity and the charge of it. Okay, now uh, and you can reverse these, and you can also write the expression for velocity in terms of radius and mass like this. So and in, right, but we have to find the expression for radius for nth. So how do we do that? So one more thing we have to consider here. So now we have to consider the quantum behavior of electron. Okay, so all of you are familiar with de Broglie wavelength. So Louis de Broglie said that all the fundamental particles, electron, proton, they have a wavelength associated with them, okay, which he called the de Broglie wavelength, and it's given by lambda equal to h by mv. So h, you remember, is the Planck constant, and this is the momentum of the uh, particle. Okay, so so this is the deep problem. Now from here, uh, you can substitute for v this value, right? H by m lambda, right? So if you use this here, what will be the expression? It will just be opposite. So I mean, it will be upside down, r, and mass cancels, under root n h pi, right? Okay, now one more thing you have to consider. So this electron, as de Broglie says, if it's moving, I mean, if it's behaving as a wave, okay, it's a matter wave, then uh, suppose this is a representation of electron, and okay, this is the position. And if it's behaving as a wave, for stability, I mean, it should be a standing wave, right? It should not. It should not. So. I mean, whatever the wavelength of this wave is, I mean, it should be an integer multiple of uh, the circumference of the circle, right? Which is 2 pi r for nth orbit. This is the condition for the stability of this orbit, right? Otherwise, you know, the phase won't match, and this the atom will not exist. Okay, so let's use this value of lambda here. So what do we get? 2 pi r n equal to nh, right? And then we can take the 2 pi down. So you will get radius is equal to, and here also we have an r. So if you square both sides, this r will cancel, and you will get n square, which is square 7 pi pi n square, right? So you see that the Rn is proportional to n square, not 1 by n square. So D is the correct answer. Okay. Thank you. So yeah, it's a little derivation that we did. Okay, if you have any question here, you can ask. If not, we can go to the next problem. Okay, I don't think anyone has any question. You can interrupt me anytime, and also you can unmute yourself and ask any doubt you have. Okay, please do not hesitate. Okay, let's go to the next problem. Uh, so the question is, what is the energy required to ionize the hydrogen atom from the third excited state if ground state of hydrogen atom is has the energy minus 13.6 electron volt. Okay, so do you guys remember the expression for the energy of hydrogen atom? So the total energy of hydrogen atom is uh, basically for any two charge system. It's given as this. Okay, r is the distance between them, and then we can put the radius from here that we have calculated. We can insert here, and we will get this expression. So this is h square, this is n square. So this formula is purely from electro electric uh, electrostatics, as you can see. You must have studied it in your class 11th or 2, and we just substituted the expression for the radius that we calculated in our previous problem, right? And this whole thing is a constant, and if you put everything, so mass of the electron, Planck's constant, the value of electronic charge, you will get this value minus 13.6 electron volt. Okay, and then you have 1 by m square. So this is the expression for energy of energy required to this is the expression for hydrogen energy of hydrogen atom. And if you want to ionize a hydrogen atom, you have to put this much energy uh, inside the system to separate it completely. Okay, uh, and this depend on what excited state your electron is. So if you have your electron in the third excited state, that means n equal to 3, right? And so you can just substitute here. Right? What will be the answer? I think it's 1.5. But why it's in positive? Why the answer is in positive while our calculation is in negative? Anyone? Can anyone tell me? So the reason is, so this is energy loss index. Yeah, so ionization energy is the energy. Uh, ionization energy is the energy that you have to provide to the system. So that's why it is positive, right? I mean, it's just the magnitude of this quantity. This is the, you know, this is the convention from thermodynamics. Like, if you have to provide some energy to the system, it's positive. If you take out the energy from the system, it's negative. Okay, let's go to the next question. Okay, so this is a problem on error, percentage error calculation. So it's a very easy question. So the percentage error in the measurement of mass and speed are 2% and 3%. How much will be the maximum error in the estimation of kinetic energy obtained by measuring mass and speed? So we know the formula for calculating the kinetic energy, right? And then we have to transform it in terms of uh, I mean, we have to transform it so that we can calculate the percentage error. So how do we do that? So I showed in the last lecture also, we can take log both side. So log of k is equal to, so since these three are multiplied together, uh, we can separate them like this, right? And log of v square we can write to log of v, right? This is the log form, and then we can do a partial differentiation. So that will give us dk by k is equal to, this will be 0 dm by m plus 2 q by v, and since we want percentage error, we can multiply it by 100. So percentage error in k is equal to, and we know that the percentage error in mass is given 2%, and in the velocity it is given 3%, so 2 into 3%. So the answer is 8%, right? Simple problem. Okay, so let's, I hope there is no want me to explain again. Okay, so what did you not understood? So you know how to take log. So log of AB is equal to log of A plus log of B. This is what I have used here. Okay, and then when I did the partial differentiation, because half is constant, it goes 0. right? And then partial differentiation of m log m and log e is like this. So you know that log of sorry d by dx of log x is 1 by x, right? You all know this. This is what I have used. Okay. Did you understood? No? Or if you have any doubts, then yes. Okay, so let's go to the next problem. Uh, Here the question is the unit of percentage error is, so is it same as that of physical quantity, different from that of physical quantity? Percentage error is unitless, or errors have got their own units which are different from that of physical quantity nature. Here B and D are the same option, I guess. Okay, so what do you think? Any guesses? C. Any more? Anyone else want to guess? Okay, I guess everyone is saying C. Yeah, C is the correct option, basically. Because percentage error is what? It is, dx by x into 100. So whatever the unit of x is, it gets cancelled from the numerator and denominator. So that's why it's unitless. Now, the seventh question. The magnitude in difference between individual measurement and true value of a quantity is called, what it's called? Absolute error, percentage error, relative error, or zero error. So these are just simple, facts that I want to recap. So, any guesses? Sai Teja says A. Anyone else? Anyone else want to take a guess? Everyone is saying A. Okay. Yeah, it's absolute error. And if you divide the absolute error by the measured value, then it becomes the relative error, right? So, and I already showed you what percentage error is. And then you, like, if you multiply it by 100, then it becomes percentage error. And the zero error is a different thing, which is related to the instrument that you are measuring with. I talked about zero error in the beginning also. the last lecture. Okay, thank you. Let's go to the next problem. Uh, the question number 8 is so a physical quantity x is expressed like this. Okay, the percentage error in the measurement of A, B, C, D are given as 1, 2, 3, and 2%. So what is the maximum percentage error in the measurement of x? Okay. So again, this is a similar kind of problem, like in, like we had in the sixth, in the question number 5. So, so I'll just this time I'll just write out the expression for the error. Uh, I will not derive it because I've already showed you how to derive it using taking the log on both sides. So the percentage error will be written like this, because B has whatever the power of the quantity is, that will be multiplied with it. That's the property of the log. So I see plus, and for because we need maximum error, so we have added all of them and multiplied by 100. And if you put everything, so 1% for A, 2% for B, 3% for C, and 2% for D, you will get 7%, right? Anyone has any doubt here? If not, then let's move to the next problem. Okay, so this is the first problem based on the significant figures. So, do all of you know what significant figure means in the measurement? Is everyone familiar with the concept of significant figure? Okay, let's go through this question, and then I'll ask what do you guys think. Okay, so the question is, the sides of the rectangle are given as, so the length is given 4.215 centimeter and the breadth is given 2.08 centimeter. Okay, and you have to write the result of the area of the triangle in appropriate significant figure. Now, I'll ask everyone, what is the significant figure in this length and the breadth, respectively? Can you tell me how many significant figures are there in the length and in the breadth, respectively? Length 4, okay, 4 and 3, okay, Yeah, you're right. So it has four significant figures, it has three significant figures, right? And then when we calculate the area, the by multiplying both, so suppose you will use just a calculator, you will get this answer. Okay, but can you report this answer? Is it accurate to report this answer? The answer is no. Why? Can anyone tell me why? Why we cannot report this answer? It's because, see, we have measured this area using this quantity, breadth and length. And yeah, and this, okay, so Parshuraman said it is more than 5. So we add 1 as 8.77. Yeah, that is called rounding off. Uh, yeah, but the reason we cannot report it as it is that because it is calculated using this quantity and it has only three significant figures, right? And so I mean we don't have the precision beyond two digit after the decimal. So whatever we calculate from this cannot have precision beyond two digits. So we can only report it up to three significant digits, that is 8.76. But what we can do is we can round it off. So we know that after 6 there is 7, so we can round it off as 8.77. Okay, so this is the law. So the answer is this. Is it fine? Anyone has any question? So this is the concept of significant figures. Okay, so there are more questions, it will become clear. Uh, so here is another question. So a car covers a distance of 2458.56 meters in 121 seconds. The speed of car in appropriate significant figures is, again, it's the same kind of question. So we know that speed is distance by time, and it's the average distance, average speed. So, and if you calculate it using a calculator, you will get a value like this. Okay. Now, again, what will you report? How will you report it? Because we have three significant in the figures in the time, in the calculation of time. So again, we will have to only report it up to three significant figure, and we cannot. And since after three there is one, so we cannot round it off, round the three to four. So this is the answer, right? Meter per second. Is it okay? Okay, here is another similar problem. So we have given the length, breadth, and height of the void, and we have to report the volume in appropriate significant figure. Okay, so volume is what? Length, breadth into height. If you calculate it, you will get this value. And how will you report it again? Anyone want to guess? This is very simple. I just want everyone to guess it. No one want to try? B. Okay. Yeah. Yeah, you're right. You can write it. No, A is not correct because we have only three significant figure in the calculation of the length. So we will only have to report it up to three significant figure in the answer. So 11.54 centimeter cube is the correct answer. We just rounded off 3 to 4. Okay. So let's go to the next problem. No, this is another interesting problem. So we have to round off 1, 3, 8, 9, 4 to three significant figures. How would you do that? Anyone want to take a guess? In A, B, C, D, what will be the correct answer? Sai Teja says it's B. Anyone else? So there is a rule that if you are so significant figures, if you are writing a number, so suppose you are writing like this. So here the significant number will be only these four. These three will not be the significant uh, digits. Okay. So if you want to write these in terms of three significant figures, we can round it off to the nearest, nearest number, which is this, which has only three significant figures, right? We cannot round it off to 138 because this is too far from here. right? Okay, I hope it is clear. So let's go to the next problem. So the next problem is if the number 0.00133757 is rounded up to four significant figures, what will be the answer? Okay, so anyone want to take a guess between these four options? Sai Teja says it's A. Anyone else? No one else want to take a guess? So, what happens in case of decimal numbers? So, suppose you have something like this. Here, the significant figures will only be these three. Okay, these are not significant figures. Okay, so yeah, that either so either you can take these three significant figures in this case, and if you have a number like this, then only this will be significant figure. The zeros in the terminal side don't contain the significant figures. If there is a zero in between the number like this, then it will be counted as significant figures, but not if it is on the terminal sides. Okay, so this you have to remember. So if you want to round it off to four significant figures, we can write it up to 4 digit here, and we can round the 5 to 6, right? So C will be the correct answer. Did anyone guesses C? Yeah, Mufida said it's C. So yeah, you were right. Okay, anyone has any doubt here? This is just to recap. Uh, these things you must have uh, learned very earlier. Okay, so I think we have our last problem for today. This is again from the hydrogen atom. So the energy of an electron in excited hydrogen atom is this. Okay, so energy is given. Electron. Now, according to the Bohr theory, uh, the angular momentum of the electron is, okay, so we have to calculate the angular momentum. Angular momentum is given by L. So do you know what is the formula for angular momentum in Bohr theory? Anyone? No. MBR is the classical formula for angular momentum, right? What is the angular momentum formula in both theory? So we know that I showed that for wavelength you have this formula nh by 2 pi, right? Oh, sorry, nh by mv, right? So mv is nh by lambda, and what is mv? It is the momentum. So momentum is nh by lambda, right? And I told you guys that lambda we can write 2 pi rn by n, right? So what will happen? Wait. So you remember this was the step. This was the condition for stability, right? N lambda is equal to 2 pi r, correct? So that's why I wrote. I substituted lambda equal to 2 pi rn by n, and so this gives us n square h by 2 pi r, and you can multiply rn to p, and so this will be mvrn, and as someone mentioned, mvr is what? It is the angular momentum, right? So sorry, let me write it here. N square h by 2 pi, but as it should not be n square h. I think I have made some. Oh, sorry. This n should not be there. This n is not there. Let me do this again. Yeah, this is correct, and this is correct. So the formula for uh, wavelength is h by mv, right? This is the de Broglie wavelength, if you remember, and mv equal to h by lambda, and we can put the lambda from here. So mv equal to 2 pi rn by n, and we can multiply Rn here. So mv Rn equal to nh by 2 pi, and this becomes the angular momentum nh by 2 pi. Okay, now this is the formula for angular momentum, and we have given the formula for energy. So how can we determine from the energy the angular momentum? So only thing that is missing here is the n, right? And we know that the formula for energy is 13.6 1 pi n square electron volt, right? So let's put the value here. So n square is just and if you calculate it, it will be 25. So n equal to 5. So you substitute n equal to 5, what you get is L is equal to 5h by 2 pi, which is D, right? Sorry to mess it up earlier, but now it's correct. Okay, so did you understand what I did? I just substituted the value of the energy in this formula that we had from earlier, and we calculated the n, the principal quantum number, and then we had the formula for angular momentum, and we substituted the value of n, which gave us the answer, right? Is everyone fine with this calculation, or anyone has any doubt? Okay, thank you. Yeah, if you have any doubt, we can ask. So this is our last problem today, and if you had any doubt in any of the problem that I discussed today, please ask. And so also this slide will be uploaded to the NPTEL, and you can find the link in the NPTEL course website, and also the recording of this video for you to refer later. Okay, so if you have anything ask, you can feel free to ask. Otherwise, we can close the meeting and meet again next Saturday. Anyone want to ask anything? If not, let's close the meeting. Thank you all for joining. Bye.